Hello and welcome. I'm excited to show you how SDN Launch Control is transforming the way we set up and manage software-defined networks using everyday hardware. Let's dive into how this innovative tool makes advanced networking simple and accessible to everyone. Please keep in mind this is an alpha release of our pre-production software that we have made open source to start sharing our progress. Please check our GitHub repo link below for regular updates. SDN Launch Control, or Launch Control for short, is revolutionizing the deployment of software-defined networks by making it accessible and affordable for everyday users. This open-source tool harnesses commodity hardware like old laptops and Raspberry Pis to set up robust SDNs using automation. It replaces complex terminal management with a user-friendly interface integrating OpenFlow, Open vSwitch, and convolutional neural networks for smart traffic classification and automated quality of service management. This tool empowers users to manage and optimize their networks easily without the hefty price tag associated with traditional SDN setups. In this video, I'll be walking you through how to set up an SDN using the Launch Control software. We'll be using physical hardware in the form of a Raspberry Pi, an access point, and USB to Ethernet adapters. In the image on screen, you can see the setup. The black box is a Raspberry Pi with the traditional built-in Ethernet port going to the normal network, and two USB to Ethernet adapters, one connected back to the network and one connected to the PoE injector of the access point. All the yellow cables are your SDN connections, and the black cable is the traditional networking connection used for communication with the SDN controller. The first step in the setup is downloading the SDN Launch Control software from the link provided below. I'll be running the demo from an Ubuntu 22 desktop environment, as that's what the software has been tested with. You can also follow the instructions in the README on GitHub. Once you have the code downloaded, open the repo in a terminal window, and we're going to navigate to the backend and then the control center folder. Once we're in there, we're going to run a convenience script that will install everything you need to run the backend. Just note that before doing so, ensure you have the prerequisites installed, which are Docker, Node, and NPM. Node and NPM will be used for the front end. This installation may take some time depending on your machine and your internet connection, so I'm going to speed it up. Once this installation is done, open another terminal window in the root folder of the repository and navigate to the UI and then control center folders, and again we're going to run a convenience install script which will install everything you need to run the front end. Once we have installed everything, we're going to use the run convenience bash script in each of these folders. So we'll start these up, and the back end and then the front end will start for us. So once both of these have run, we will be able to open a browser and go to our local host on port 3000 and view the launch control front end. Once we have everything installed and set up, we'll be able to set up the network using the hardware I showed at the beginning of the video. So currently this user interface has no devices connected to it, as you can see there. So if we navigate to System and then Install Software, we're going to install Open vSwitch, which will turn our Raspberry Pi into an SDN switch. So give it a descriptive name. This can be anything. We're then going to fill in the LAN IP address of the Raspberry Pi, so just make sure you know what that is. We're going to fill in the username and password we use to log into the Raspberry Pi. Select the operating system, which is already pre-selected there, the device type, which will be a switch, which is pre-selected there, and then the API URL is very important for us to fill in so the Raspberry Pi knows how it can communicate with the actual SDN launch control software. So make sure you give it the IP address of the machine running the launch control software, and don't forget to fill in port 8000 at the end. So http://10.10.10.81, and then you'll see I forgot the port number here, but that's very important. So again, :8000. Once you've clicked install, you'll actually be able to open the terminal window and see all the different things that are happening on the back end. So installing OVS on a Raspberry Pi is quite a long process, as it will download and then build all the required code. So this may take some time, so just be patient. For the video, I'm going to speed up this installation process. So eventually you'll see a little pop-up saying that OVS has been installed, but the loading icon will carry on as other software is being installed on your switch, so you can monitor device resources. So this will take a little bit of time as well. So carry on being patient. I'm going to speed it up for the video again. Finally, once everything is installed, you will be able to open the sidebar and navigate to devices, and you will see that the switch is now listed there using the IP address and the other details you gave when installing OVS. But for now, we're going to say on the system install software tabs, and we're going to install Onos, which is a open source SDN controller that we'll use to manage our network. So I just have a virtual machine running Ubuntu server that I'm going to use as my target device. So 10.10.4 is the IP address of the virtual machine. I'm going to put in the username and password that I use to access the virtual machine. And again, the API URL is just the IP address of the actual machine I'm running the launch control software on. So http://10.10.10.81 or 82 in this case. And then don't forget to add port 8000, which I forget to do here in this video, and that will result in some issues. So just remember to add :8000 at the end. Once this is done, we are going to navigate to our devices page. So you'll see that our two devices are listed. I'm now going to click on the actual cog icon, and what happens now is we establish a connection with the Raspberry Pi to ensure that all changes made on the UI are properly configured and actually implemented on the device. So if we scroll down, we'll be able to see the device stats. So this is just a real-time graph showing your CPU, memory, and disk usage. But for now, we're going to add a bridge. So we're going to add a bridge on our Pi, which will add two ports, Ethernet 1 and 2, which you saw in the original picture, which were those USB to Ethernet adapters, and we'll connect it to the Onos VM. So the API URL, again, very important. So it's our IP address followed by port 8000. We're going to select our two ports, which are ETH1 and 2. And we're going to select the controller. You can leave the controller port as the default one usually. So the creation of the OVS bridge won't take that long, but the overall setup process may take a little while, as there is also another resource monitoring tool being installed and created on the switch, which will allow us to monitor the traffic moving through ETH1 and ETH2 on this user interface. Once we have a notification that the bridge has been added successfully, we'll be able to view our bridges and edit them if we want. Again, whenever you see a loading icon like this, it usually means that there's been a connection established between the device and the software to ensure that any changes that are made are reflected in both the software database and on the actual machine. So now we can select that bridge and view the port statistics. At the moment you can see that there's only 0.06 megabits per second moving through one of the ports. So the next step is to set up our Onos controller so it is able to install OpenFlow rules on our switch and enable our network to start functioning fully. To do this, we're going to navigate to the Onus UI, which is hosted by the Onus virtual machine that we set up earlier. So we can go to our menu again, and we can go look at the hardware and then controllers submenu. On this menu, you will see our Onus VM that is currently controlling 10.10.10.3, which is the IP address of our switch. So we're going to navigate to the Onus UI. I'll link this in the description, and you just replace 10.10.10.4 with your Onus VM IP address. Once we've logged in with the default username and password, where the username is Onus and the password is ROX, we'll be able to go and install applications. So we'll install the OpenFlow application on Onus and the reactive forwarding application on Onus. And this will allow for our controller to actually connect with our SDN switch. So the OpenFlow app enables OpenFlow communication with the Onus controller, and reactive forwarding essentially allows our switch to act as a layer 2 switch. So once we've installed these apps and we've enabled the communication between our switch and our controller, we'll be able to go back to the topology view on Onus and actually see the device, and we can see both our ports are showing up there. So now we're going to go back to our launch control software, go to hardware and then devices. We're going to connect to our device, and I'm going to display what happens now when an actual device connects to the access point. So I'm going to connect my phone to this access point and run a speed test. So initially we can still see there's very, very little traffic running through the ports. So you can see it's only going up to 0.8 megabits per second. But now that I've connected my phone to the access point connected to the switch, the throughput is going up, and I'm going to run a speed test. And my internet connection is usually 300 megabits download, so you can see there it's shot up to around 300 megabits per second, and there's a slight increase in the CPU usage on the switch. And my upload speeds are usually around 150 megabits per second, so we're going to see the CPU usage spike again as the upload starts, and it reaches that 150 megabits per second area. So once we have our SDN switch and SDN controllers linked and everything configured, we're going to install some plugins. These plugins will enable our machine learning quality of service tools. So you can read about them by clicking on the description and information icons. So we're going to install the traffic classification sniffer first. So again, the API URL, we've gone over this, but it is the IP address of the machine hosting the launch control software, followed by port 8000. A monitoring interface is ETH2, which is the port that is connected to the access point. And this is the second port, and then port 1 is connecting back to the internet, so the WAN port. And while it is labeled as the WAN port, it doesn't need to be the physical WAN port that is connected to your ISP provided internet connection. It just needs to be a port that can get to the WAN port and connect to your firewall if you have one and send data to the internet. And once we hit install, this will install a traffic sniffer on our SDN switch, which will communicate with our traffic classification algorithms running on the back end and essentially enable encrypted traffic classification. This installation process will take some time, as it is not only installing the sniffer, but also building it from source on the device. So once it's done, we will install the other plugin, the Onus Traffic Classification plugin. So essentially this plugin will allow you to create categories into which your traffic will fall if it is classified as that particular app, and we'll be able to rate limit those applications, which I will show you an example of once it's installed. So once installed, we can go to our monitoring hub and watch traffic classifications coming in. So I'm connecting on my phone. I'm going to access services like Spotify and WhatsApp and Instagram. And this is just me connecting to the access point, and you can see all the different services showing up. This is all in real time. What we can do is go to AI services and go to traffic classification, and we can add a meter. So a meter is essentially a category into which we can assign applications. So if I wanted to stop Instagram from working, I could create a meter entry at 1 kilobit per second, which would result in traffic being limited to 1 kilobit per second when it's classified as Instagram, essentially blocking the traffic. I can carry on making other meter entries for different applications. So I'm going to create one for YouTube where it is limited to 1,000 kilobits per second. So now, in real time, these traffic classifications are happening, and they will be restricted to these speed limits at a per flow level. If I navigate back to the lobby and then the dashboard, we'll be able to see a network topology diagram, which is actually independent of the controller and navigates through open flow rules in the SDN switch to find the details about the devices and what's connected. So we can see the ONOS VM, the Raspberry Pi switch, and the devices connected to the access points. Thank you so much for joining me for this demo today. I hope it has inspired you to see the potential of SDN launch control and the capabilities of a management software like this that steps away from proprietary hardware and makes networking management open source and ubiquitous. Please don't forget to give us a follow on our social media and contribute to the GitHub repo if you're interested in the project.